Okay, this is video number 18, I think. There's not many more videos in theory and within theory and example, maybe 3 or 4 more, but I need to go over this with you. So in my previous video I showed you what is a three-phase transformer, what are the configurations, what are the currents in those transformers depending on their configurations, whether they were Y configurations and delta configurations. Sorry for my bad English. Okay, we did that, but nothing spectacular with that, because it's hard to calculate some things with a three-phase system. So we usually refer three-phase system into a single phase. Why? Because it is easier for us to understand the principle working, because this is fundamental learning. This is not advanced transformer course. This is for students who are learning the transformer theory for the first time. So we can refer to a single phase transformer, and I'm going to show you how it is done. So let's start. I have 4 pictures, 4 drawings over here. This is drawing A, drawing B, drawing C, so drawing D. We're gonna go it alphabetically, so A, B, C, and D. Now, first we are going to concentrate on this one, which is, I hope, familiar with this. You have in my description the playlist link, so you can go. You can go 1, 2, 3, 4. You don't have to jump from 17 to 5, or you can go, chronically. I think that's a good word, chronically, maybe. But you get the point. 1, then 2, then 3. So here we are in the 18th video. Now, in my previous video, you saw, I hope you watched it, that what is a Y delta configuration. Now, when we learn transformers in a three-phase, this is the most, I don't know if it's practice, it is the most common configuration, but this is where we do some examples and problems. When we learn, this is like the most common configuration we can have. Because in households you always have nearby, in your district area, you have transformers that lower the voltage. So that's what we are doing. Okay, now I think this is all familiar with you. So we had current I, line voltage V, and the voltage induced here is V times square root of 3. So on the line voltage we have, in the line voltage on the delta configuration, this was the voltage, I hope you remember that, and this was the current. Now, if we have a delta, 3 loads that are usually the same. Now, when we are learning electrical machinery, there is, for example, an induction motor, which all 3 phases have, in practice they don't have, but they have the same load, which of course in real life it isn't, and in household areas, district areas, industry, of course, not all of these are the same, but let's say they are the same. So we have the balanced 3-phase voltage, the balanced 3-phase load, if the voltages and the loads, ZL, are balanced, then the currents in the 3-phase system is also balanced. In every phase, the RMS values are the same. Okay, now remembering something, if you have learned in first year about fundamentals of electrical engineering. If you have a delta configuration with ZL that are also all the same, we can transfer that to a Y configuration, which is equal to ZL divided by 3, ZL divided by 3, ZL divided by 3. That's hypothetical, but it is true. But if this and this you want to have the same thing, then this is equal to this and this is equal to this. I hope that is understandable for you. And the loads from delta side are connected. Okay, I said it like 5 times. But why do we do that? We want to transfer this delta configuration into a Y configuration, because then we can easily refer this to a single phase. Just wait a second. So, on the output we want to have the same line current, and we want to have the same line voltage, like here. So what changes if we want to transfer this to a Y configuration? Well, if you want this and this to be the same, look, in the delta configuration the line voltage is the same as the phase voltage, but in Y configuration that is not the case, because phase voltage in a Y configuration from here to here, that's the phase voltage, is the line voltage divided by square root of 3. So when you divide this by square root of 3, you get V divided by 3A. Okay, now, and the current here stays the same, here and here. So the induced current over here is equal to here. And we transfer this into a Y configuration. Now, the phase voltage over here is same as here. And the line voltage from here is same as here. Because line voltage over here, from this, let's say this is phase A, this is phase B, is same as here. And that is over here. So this is, now we transfer this to a Y configuration, delta to a Y. Now we have a Y and Y configuration, which is used in, for example, induction motors. Also we refer a lot of things. Why do we do this? Because the calculations, computing things are easier. Now, the phase voltage over here, we can now write the single phase equivalent circuit. Now, the phase voltage over here on this particular, now we want to have single phase equivalent circuit. So we can calculate the line current and the voltages much easier. And the phase voltage on the primary side is equal to line voltage divided by square root of 3. And on the secondary voltage, it is equal to V divided by 3A. So now what do you see here? This is not square root of 3, so there is another turns ratio, which is called okay, so now there is a different turns ratio that is equal to Ny divided by N2 divided by square root of 3, which is equal to, this is a new equivalent Y to Y turns ratio that is equal to square root times A. As you can see, this here goes on the denominator, divided by the denominator we have, and this is N1 divided by N2 is A. This goes it's a double fraction, and this goes in the denominator, and then you have another turns ratio, equivalent turns ratio, that is equal to square root of 3 times A. A is equal to Ny divided by N2. So this is now, if you have a three-phase transformer, Y delta configuration, we can transform it like this. Okay, and that's it. And this load is equal to 0 divided by 3. Now, with this, if we know what is the load, what is the turns ratio, we can easily calculate the currents induced on the output of this transformer. For example, we can now know what is I on the secondary side, which is equal to this. And you know, you will see in my next two videos, I'll give you an example. In my next two videos, we are going to do two examples of a three-phase transformer. So I hope, now this is the picture from that one, refer to that single phase. That's it. Thank you for watching, and see you in my next video. Bye bye.